So I'm going to start and then we'll turn it over to Lauren after my section. And I'm going to just dive into a little bit of background about the project itself and explain this kind of collaboration that we were able to develop and how all of the pieces work together. I want to start though by saying it's Lauren and I are here representing the project today, but it was a huge cast of characters. You can see many of the names in front of you, and then we also involved a lot of graduate students in Greenland and many, many community members, each one of which had a huge contribution. And actually, when we were writing up the contribution page for some of the work that we're doing, we had a massive document, which is wonderful. That was really what it was all about. I'm going to start with just talking about Greenland's ice for a minute to kind of set the stage. So, 80% of Greenland is covered by ice and has been for over 1 million years. And of course, that's really fascinated those of us in the Western part of the world who are really focused on answering those cool questions about how has it changed through time? You know, what's driving those changes through time? How might it change in the future? That's really been kind of our focus, and primarily we're thinking about how is that going to affect us? But not a lot of us have spent a lot of time thinking about the Greenlanders themselves and what might be the questions that they are asking. And so that was the focus of this particular project, was to look at changes and try and work with the communities there to see it through a different set of eyes. So in terms of the people that are there, it is a really fun group of individuals. They're very unique. They are mainly Inuit. They are focused around the edges of the ice sheet, so there's not any means of getting directly from place to place unless you're involved in the maritime area. So you want to be using the oceans and or air travel to get around. They jokingly say there are only, and this is true, but they joke about it, that there are only two streetlights in the entire of Greenland, and those are both in Nuuk. So it is very focused on the oceans and the marine systems. And so looking at what's going on with sea level change there and how it's affecting their communities was really important. I do want to mention that it's an autonomous territory. It is in the Kingdom of Denmark, but they do have their own rule. And they are very proud of that, and they make their own decisions. They depend quite a bit on Denmark for some logistical support, for a lot of their financial support, but they are making their own decisions. Their population is not large. Almost, they're pushing towards 57,000 now as of 2024, and I don't think it's changed a whole lot since then. But most of those people are situated in just 16 different towns and then 54 smaller settlements. And the difference between a settlement and a town is just that the towns have its numbers primarily, but the towns also have some kind of representation in them, whereas the settlements would send a representative to that town for their representation. Of the like 56,699, we just need one more, we get to 700, right? 33% of those live in Nuuk. So it is not evenly distributed by any sense. It's very much southern focused. We're kind of down here. So Nuuk has, a third. And then the next largest community has about 6,000 people. So it's quite a spread in terms of where you might find people. And again, you can see that primarily they're on this west coast with just a couple of little settlements and towns over here on the east. And then much of the east is a national park system. Most of the people are Inuit. There's a lot of Inuit Danish mix, and they consider themselves both Danish and Greenlandic citizens in that situation. And then just about their priorities, again, we're just setting the stage so that you can kind of understand how we were able to work together. They are very dependent on Denmark for their economics, as I mentioned, but locally, they're very focused on fishing. So fishing is their primary economic piece. Uh, they not only depend on it for their livelihood, but they also look at it as a way of life. I mean, they are completely focused on the water, as I mentioned. And so everybody has a boat. I mean, it's highly unusual. It's actually a real hardship if you don't have a boat. And those people that might lose their boat in a storm or whatever, that really makes their lives really challenging. So very much focused on the water. For the meetings that we had with the communities in Greenland, remember I said our priority, of course, is changes in the ice and understanding how that's affecting the land, et cetera. For them in the communities, it was really how is this going to affect their fishing? They were very much focused on that as part of the meetings that we had. And at the municipal level, it was a little bit of a switch into how might that affect shipping, harbors, and piping, because remember, everything is maritime based. So they are very much trying to figure out what might be the changes coming their way. Okay, so that's kind of setting the background, and now we'll get into actually talking about the project. So the official name of our project was Predicting Coastal Responses to a Changing Greenland Ice Sheet. We've always gone by Greenland Rising. It's a really great, acronyms don't work if you're working between cultures, so having a name that has some meaning to it is really important. So for us, Greenland Rising, for them, Galashat Nunat Kafapak, you can easily explain, what are we focusing on? Why are we studying this? And it gives you a chance to kind of talk a little bit about the science and make it in a way that's relevant and actually accessible to them. The project itself was a partnership. So it was a partnership between, we started with two Greenlandic institutions. We ended up working with just one, and that was the Greenland Institute of Natural Resources. So they were a key partner. The community members themselves were partners. And then our own researchers here were partners. So there were these three partnerships, and we focused on three different communities, Kushoshwak, which is the furthest north, Asiat, and then Nuuk. And then we had three different components. So we were very much tied to the number three, I see. We looked at first the natural environment and how that was changing. And Lauren's going to spend her time talking about that, looking at how we were able to use data to develop these models for past, present, and future sea level. The second component was focusing on collecting bathymetry information and helping them to match that bathymetry to habitat maps. So we were able to kind of develop these habitat maps for how these changes in sea level might be affecting these different habitats, as well as how this might affect ports, shipping routes, and et cetera. And then the third component was about working with the community, engaging with the community in a meaningful way, getting their input on all of the work that we were doing, and then also bringing STEM education into the area. And so those are the words that explain it, but a very Greenlandic way of doing it is just to throw images up. Language is not their primary communication piece. They love to communicate through imagery. And so this is the same thing that I just said, and I'll show you how we can do that or parse it apart. So here we have part of the GNet station that's up in Kushoshwak. So this would be the piece that would speak to the changes in the natural environment. So how is the Earth responding to changes? And here we're installing a tide gauge, which will help us get the same thing. The second part was the bathymetry. So here we have a section of bathymetry that was collected by their Sana, which is their ship. And you can see Akaluk up here in real time collecting that data. Over here, we see that third category, which was working with the community, gathering their input. And then this is a piece from our STEM education. So again, just a different way of doing that communicating. And that was really important to us because as we were getting ready to deliver back a product at the end, we needed to know what's the most meaningful way to actually do this. Okay, so the project itself is centered on Greenland and it's really focused for Greenlanders. So what does that actually mean? So for us, it meant that every single community we worked in was a full partner. And they were a partner from very beginning, from project design through the implementation into the final product. So it wasn't just, deliver something and give it to them. We really wanted them as part of this. We really centered on people first. Language was huge. We wanted to be able to communicate with them in Greenlandic, and thank goodness for our Greenlandic partners who were the people that allowed us to do that. We really wanted to have purposeful engagement, so we really wanted to have these connections on a regular basis. We prioritized in-person connections. So we committed to 4 different visits to each community during the course of this. And that's a lot to commit to at the distances we were working with. So we went into each community in the very beginning to gather input, to put together the ideas for what we were going to be doing. Uh, During the project, we went back into the community and worked with the community members to collect the data and contribute to the data. And then after we had the data, we actually committed to 2 follow-up visits, one which was more of a deliver listening meeting, and then the final one was to really provide this information back to them. And then we had to adapt. We hit COVID right off the bat, and so we had to rely a lot more on our local people. But we managed to make it through in large part because of the people there and how wonderful they really were. Um, so building connections was something that was different in each community. In Nook, we actually had, because it's such a populated area, it's much more like an actual city. And so TV coverage and national newspapers made a lot of splash. We were able to reach quite a few people um, at that level. However, there are still a lot of people that don't listen to this kind of news. This was very sciencey. And so we also did some community outreach. We spent a lot of time we went to the mall. You can see a couple of these are taken at the mall. We did outreach events at GINR. We really tried to connect with the community when we were there and talk to people and learn from them. So we wanted to tell them about the project, but also wanted to get input from them and hear from them. In Aasiaat, their main communication happens to be a local radio station. And so working with Nini, who was one of the grad students that we worked with, who's from Aasiaat, she got Akaluk onto the radio station so that when we were there, we had a chance to reach out broadly to the community and invite them to come and talk to us. So invite them to these meetings. And in Kushwashwak, it's really just go there. It's one of those places, it's very remote. And so you land there, you commit to spending time there, you spend time in their lives. This was a particular event where they were doing sled dog races. And so the team was there to kind of integrate into the community and become, build relationships, which is what it's all about. And then in every single community, we also worked in the schools. So we worked in the high school and we worked in the upper elementary, which for them is like 8th and 9th. We developed some STEM curriculum in Greenlandic. So we worked with them to do the translations into Greenlandic. And then this is Ulak, who was able to teach it in Greenlandic directly to the students. As you get out of Nook, there's not much English. And so it's really important to have Ulak, Marina, Akaluk, all these people that could actually do that communication for us. Okay, so I said it was a series of 4 visits, and I'll just kind of go through what were some of the priorities. So the first visit, the real priority was just meeting with people and learning from them, understanding a little bit more about their community, building trust, and figuring out how we could work together. So sorry for this image, but the meeting in Nook was during COVID, and so all I had was a Zoom picture. But the first meeting in Nook was primarily with representatives of the municipality and the government ministries. Again, this is a larger community. It's the capital and government seat of Greenland. Because it's so much larger, it's much harder to actually meet with community members. We had a hard time trying to get together with the Fisher and Hunter Association. There's a lot of concern about maybe learning too much about how they're fishing and hunting, and it might restrict their ability. And so we just went with what we could, and that was working with the municipalities. And that was great. They had a lot of concerns about infrastructure changes that might be coming their way, what might be happening to the ports, how about the piping that's underground that enters into the water. And then there also is a commercial lump fishery. So we were able to get those as priority items for doing our work. In Aasiaat, this community has about 3,000 people. They're mainly fishing focused. There's a large fishery there. And so the municipality leaders were very involved, but also the hunters and fishers were more than willing to meet with us, which was a benefit of having Nini involved. her father is a hunter fisher, and so that enabled us to kind of open the door there. And there, the focus was on hunting and fishing needs, as well as changes in infrastructure. This particular harbor is very shallow. There's some very narrow channels in this area. When I was there most recently, one of the large ships pulled in, and they have to wait till high tide. It took them too long to unload, and they had to wait for another tide cycle before they could get back out again. So this was definitely a concern of theirs, was trying to figure out what might be changing for them in terms of the harbor area. And then in Kushoshwak, which is not even a town, this is a little settlement, has about 450 people. This area is very much, it's a harbor area. It's an island, but the village is centered around the harbor. It's very cut off during the winter, which is long, starts in September and goes through till June. And they really live a sustainable hunting and fishing lifestyle. So that is a priority. But you can see, looking at these pictures, this same little harbor deals with these small fishing boats, but it also has to accommodate these huge ship vessels that come in. And so trying to look at what might change and how that might impact that was really kind of a priority for them as well. I did want to point out, this is a picture that I took in May 26th in 2024. So you can see that harbor area is completely frozen in still. So it is a very long winter as this far north. And so, making sure that you're thinking about what their priorities are. And this is one of their priorities, is just maintaining their fisheries. And in this particular area, they have fishing holes cut in. This is Jonas. He's a Greenlandic halibut fisherman. Uh, those particular fish like a very deep, cold water, and they are seeing some of this changing already, that they're seeing other fish move in and a reduction in the number of Greenlandic halibuts. So they were very interested in understanding how this might shift as sea level changes. And the focus of these meetings was really about planning, capturing information. You see, they were all centered around maps. We learned lots of things. They would point things out. They would circle things. They would give us steps from their own experience with just lowering these fishing lines. It was really, really important to hear from them, as well as it was really important for us to have language in these communities, as I've mentioned before. So being able to speak with them was critically important. And so this was some of the outputs that we got from these meetings. You'll see that they are very, drawing circles, sections. But these then became our priority research areas. So the Greenlanders really did tell us what was important to them, and we worked with them to make sure that we captured that data for them. So visit number 2 was when we came back to do the work, and we really focused heavily on including local Greenlanders in the work that was done. Of this particular ship, this was when they were doing the bathymetry and ground truthing. You'll see that they're all Greenlandic, with the exception of Carl, who's over here, who works at GINR, and David, who also worked there. But this was the crew, and we were really dependent on their knowledge and understanding of the area, which was really great. And as we traveled to different communities, we would bring on people with local knowledge. So this is Tumultuous. He is a very important person in Qushorshwak. He was the representative to the municipality for many years. I think he might now have stepped back from that. But getting him on the boat to help identify priority areas, even though we had a Greenlander on the ship, he didn't know this area. And so again, kind of building that relationship and bringing them in so their voice as part of the project was huge. We also incorporated several Greenlandic graduate students in the fieldwork. So all 3 of these, Ulak, Jane, and Nini, were geophysics students. And so they were able to get some experience being on the ship as well as helping us. So there's always kind of a, what can you give us back and what can we gain from this experience? So I think that was really important. And then we even had a local high school student, which was fun. We met Pilungok when she was in high school in Asiat. There are only 3 high schools, maybe 4 now, I'm sorry, high schools in Greenland. And so they don't stay in their local community if they want to go to high school. Very few of the students do go to high school, but I'll call her Pilu because that's easier. Pilu was from Kushorshwak. We met her in Asiat, and invited her to go back with us to Kashorshwak to help us. So this is Pilu back here. You can see she's not a very tall person. She was amazing to have with us. She helped with making connections. She helped with the in-class instruction. She did translations. And again, she helped us, but she really benefited hugely from this opportunity. She is not able to go home during the course of the semester because it's too expensive. So our being able to provide that was really neat for her. And she sat in on all these meetings and helped with translations, even though Akaluk speaks Greenlandic, Pilu knows the area. And so that was a really nice mixture. Visit 3 was focused on getting preliminary feedback from the community members. And so you can see this is Tumultuous up here explaining what questions he has about this preliminary data and something that he might want to see represented differently, or is there something that he could add to our understanding? There were a lot of things that came out of this. So what do they see in the data? What are we missing that they could help us understand? What could we help clarify for them? What would be more helpful for them in terms of getting this information? These meetings were so valuable. And, originally we hadn't intended to do like a preliminary feedback meeting, but it just happened that we didn't have the data together in time for what we had scheduled as a meeting. And it seemed like such a great opportunity to really meet with both municipality members and community members and hear what they needed. And so we decided to do this additional visit. And I think in the end, we were super glad we had done that. And then our final meeting was the one where we actually brought them the materials that we had discussed with them and in a format that they had. So this was in Asyad. We were meeting with one of the municipal leaders who was very interested in what was going on in their waterfront, which I know Lauren will talk a little bit more about. This was their harbor master, and she really was so happy to get this map. And then this was Carl presenting to this larger group. When we went, we were so concerned about, small variances in data that we had questions about. And when we got there, we realized that they were working with pretty much like blueprints from, many years back. And really, this was so much more information than they had had that it was really, really a huge advantage to them, and they were super excited to get it. We also delivered things back to people that helped us in the community. So this is Akalu, who was one of the small boat captains who helped us in the shallow water. We wanted to make sure that everybody that we worked with got a chance to see the final product, and we printed a map out for him and provided it. He was super excited about that. Again, education was part of every visit. So we did 4 different visits to each of the schools that we worked with, whether they were high school, we worked with a high school in Nook and one in Ossiat, or one of the middle elementary, they mixed them all together. And we had several of those in one in Nook, one in Ossiat, one in Qushorshwak. So that was really exciting. And then finally, I just want to show you in the next 2 slides some of the ways that we were able to give education or materials back. So this was, as I said, one of the biggest challenges for us was to figure out what was the most meaningful to them. And it ended up that it was this kind of a smorgasbord of different materials that would be useful to them. So I'll just go through them. This is an interactive poster that had QR codes that was tailored for each different community. It talked about the sea level rise projections for that particular community. It spoke to the process. You'll see this kind of circle. We wanted them to remember how many times we had asked for input and that we were there, and just to kind of show them that this is an open-ended process that involved a lot of discussion, collaboration. And then some of the maps, the data was there with some of what we had collected from the bottom of the ocean in their waterfront area. We did a story map for the project, and then we did a separate arm off that story map for each community. This is the main story map, and then this is the off of the Ossiat arm. In that, we embedded this data-rich piece where you can actually click on these camera images in the map, and you can see what's actually at the bottom there. So what's the habitat like, which was really fun and very eye-opening for them. And then we did a whole set of curriculum for them, which is in English, Greenlandic, and working on a Danish translation because we learned that because Danish is the language in that's the accepted language at the school system, we needed it in all three. And then a few other things that we did, developed Avenza maps, which are maps that sit on their phones. Those were developed at the end of the second visit in each of the communities and was updated after we met back with them so that the fishermen could use these. These were extremely useful for them. We delivered, excuse me, maps and reports to each of the communities. The reports were in Danish for the municipalities because, again, that's the language that they keep everything in. So trying to hit what we could in different ways. And then everything was transferred over to the Arctic Data Center. So a lot of different pieces went into this. And with that, I will turn it over to Lauren, who will talk about the actual sea level rise work, sea level change work, sorry.
Yeah, thank you, Margie, for giving some context to the project and yeah, just explaining how we worked with the communities and why this work is important in the first place. I'm going to be diving a bit more into the science side of things and how we actually created these projections of sea level change out to 2100. So just to start as an introduction, the Greenland ice sheet has been melting and is projected to continue to melt over this century. This figure shows projections from the IPCC 6th assessment report that gives mass change from the Greenland ice sheet in gigatons on the left y-axis and then meters of sea level equivalent on the right y-axis for 2 end member RCP scenarios. And the IPCC predicts that the Greenland ice sheet could contribute up to 25 centimeters of global mean sea level rise by 2100. But sea level is not going to rise uniformly everywhere. There are a lot of processes that contribute to the sea level signal that we will see over this century. Some of those processes actually add water into the ocean. So these include, sorry, I don't know why why the circle keeps appearing. Just ignore it. But these include, sorry, they change the volume of water in the ocean, or change the volume of water in the ocean. So these include things like the melting of ice sheets and glaciers, which add water into the ocean, or thermal expansion, which heats up the water, causing it to expand and take up more space. Other processes deform the solid earth or change the distribution of water within the ocean basins. And these deform sea level or change sea level locally and regionally. But this is a very dynamic system. And so oftentimes several of these processes will be interacting, or sometimes one process will trigger another. And so as an example, these figures again show projections from the IPCC, this time projections of the contributions to global mean sea level change out to 2100. And we can see that they project that the ice sheets and mountain glaciers are going to cause global mean sea level to rise. However, if we look at spatial plots of sea level change at 2100, we can see that sea level isn't going to rise everywhere from this ice melt. In fact, if we look around ice sheets and glaciers, we actually predicts that sea level will fall. And this is because ice melt triggers another process called glacial isostatic adjustment, or GIA. And GIA is actually the dominant driver of sea level change in the near field of melting ice for the most part. GIA is the viscoelastic response of the solid Earth, and then the subsequent modulation of the gravity fields and Earth's rotation to changes in ice and ocean loads. So as an ice sheet grows, it's very heavy and its weight depresses the land that it's sitting on, causing the mantle to flow out from underneath it. And so causing that land to depress downwards. And then also because we have an excess of mass on the surface, that ice gravitationally attracts the ocean water towards it. And both of these things cause sea level to rise near the ice sheet as it's growing. When the ice sheet melts, its weight reduces, and this allows the mantle to flow back underneath it, causing the land underneath the ice sheet to rise upwards. And then additionally, because the ice sheet now weighs less, the gravitational attraction of the water towards it decreases. And both of these processes, the solid Earth uplift and the modulation in the gravity field, cause sea level to fall in the near field of a melting ice sheet. And so because of GIA, we really expect the sea level signal in Greenland to look quite different from that which is projected for the global mean. So while there have been a lot of studies that look at the impacts of sea level rise on coastal communities around the world, studies that look at the impacts of falling sea level on communities that live near the Greenland ice sheet or mountain glaciers are lacking. In fact, the IPCC notes in their sixth assessment report that there's a lot of uncertainty in their projections due to GIA and due to other drivers of vertical land motion, and that in regions where these processes are important, that in order to create higher fidelity projections, we would need to do more detailed regional analysis. And so how do we include GIA in projections to create more reliable projections of sea level change for the communities around the Greenland ice sheet? Well, in order to run a GIA model, we need to know two things. One is how the solid Earth deforms when subject to a stress or the mantle rheology. Specifically, we need to understand the viscosity of the mantle, as this determines the rate at which it's able to deform. The second thing we need to know is how ice has changed in the past and how it's changing today, as these things, as this ice change impacts the observations of GIA that we see today. Also, because we're interested in future sea level, we need to have some sort of understanding of how we expect the ice sheets to change into the future. And so just looking at the mantle rheology first, in GIA studies, we typically model the Earth as a 1D viscoelastic Maxwell body. So a Maxwell model is represented by a spring in a dashpot in series. So if you apply a force, you get an immediate elastic response, which is represented by the spring, and where deformation is linearly proportional to the stress applied. And this response is also modulated by the elastic modulus. You also get a time-dependent viscous response, which is represented by a dashpot. And so a dashpot is a pot filled with viscous fluid that has a piston in it. And if you apply a stress or a force on the piston, it will move through the fluid, but that rate of deformation will be proportional to the stress that you apply. So if you pull harder, it can deform faster. This response is modulated by the viscosity of the fluid within the pot. So for a given stress, that piston will be able to move faster through less viscous material like water than it would through higher viscous material like honey. And so we generally believe the Earth to behave viscoelastically like this, with a time-independent elastic response and then a time-dependent viscous response. And for the Earth, we are generally concerned with the viscosity within the mantle, as this is the portion of the Earth which is able to flow. By 1D, I mean that we only vary the properties of the Earth radially with depth. And so we typically define one viscosity for the lower mantle, one viscosity for the upper mantle, and then we would prescribe an elastic lithosphere where temperatures are too cold for it to deform viscously. We know that this model is a simplification. One reason is that we know that there are lateral differences in Earth's properties. One way we know this is from seismic tomography studies, which use seismic waves to image the interior of the Earth, and they reveal to us these areas where seismic waves move faster or slower, indicating differences in the mantle properties, including that viscosity structure. And then additionally, experiments in the rock mechanic community have also shown us that the Maxwell model, which again assumes one viscosity per layer through time in the Earth, that this might not be the most accurate representation of what is actually, or might not be the most accurate representation of the mantle's behavior over a range of timescales. So specifically in their experiments, they show that the frequency of loading, so how fast, in our case, how fast that ice sheet grows and melts, that this can induce different viscosities within the mantle. And for shorter term events, like those that occur over tens to hundreds of years, these can induce a mantle viscosity that's orders of magnitude lower than the viscosity for longer term events that occur over thousands to tens of thousands of years. This behavior is termed transient rheology, and it's important to include in GIA studies, as typically in GIA studies, we would model really, sorry if you can hear the siren in the background. I am in the middle of New York City, so it might be common throughout this presentation. But yeah, typically in GIA studies, we model short-term events just purely elastically because the timescale is so short that we assume no viscous deformation can occur if we have the long-term steady state viscosity, which is around 10 to the 20, 10 to the 21 for the Earth. However, if a short-term event induces a lower viscosity in the mantle, then it actually can cause significant amount of viscous deformation in the Earth. And this would impact our present day observations as well as projections of future sea level change. So it's important to consider, and I just included this phenomenological model, the extended burgers, as like a counterpart to the Maxwell model to show that just one way that you could include it in a GIA model. I don't use this, and so I won't talk about it again, but it's just is one way in which we can include a transient regime of deformation in our GIA models. So in addition to accounting for complexities in the mantle rheology, it's equally as important to understand the history of mass changes. And the amount of ice on Earth has constantly changed throughout Earth's history as we cycle in and out of glaciations. The most recent period of time when we were at peak glaciation was around 20,000 years ago. And we call that the last glacial maximum. I won't replay this, but we did pass it a little bit ago. And during that time, we had a large ice sheet over North America, Europe. The Antarctic ice sheet expanded and the Greenland ice sheet expanded. And so just looking specifically at the Greenland ice sheet, during the last glacial maximum, it extended out onto the continental shelf. It reached its maximum position around 16, or its maximum volume around 16.5 thousand years ago, when it held an excess volume of 5.1 meters. And then it began deglaciating and became largely land-based around 10,000 years ago. The rest of the Holocene was characterized by phases of growth and retreats, and the last phase of growth occurred during a period of cooler climate, which we call the Little Ice Age. And so this occurred around 1400 to 1850 CE, and it was recorded in a lot of different paleoclimate proxy records. And so this just shows Northern Hemisphere variations in the Northern Hemisphere surface temperatures starting from 850 CE to today. And we can see this period of polar climate beginning around 1400 and ending in the mid to late 1800s. And during this time, the Greenland ice sheet expanded past its present day position. So this map shows a spatial plot of the difference between ice today and ice during the Little Ice Age maximum. So we can see that during the Little Ice Age maximum, the colors in this plot indicate that there was more ice during the Little Ice Age. And so we can see that there was more ice pretty much along all of the margins in Greenland. And in some areas, we reached an ice thickness of about 100 meters or more of ice thickness during the Little Ice Age compared to today. And because ice changes that occur over different timescales can induce different viscosities because of transient rheology, we actually do infer different viscosities in the mantle below Greenland for these different events. So this is a study done by Paxman et al. 2023, and they inferred the viscosity of the mantle below Greenland and showed that for the Little Ice Age, or events that occur over hundreds of years, the viscosity of the mantle was inferred to be around 10 to the 19 Pascal seconds. And this is about 1 to 2 orders of magnitude lower than the viscosity for longer term events like the last glacial maximum. I also want to note that for the longer term event, for the last glacial maximum, we do see larger lateral heterogeneities in the viscosity structure than compared to the Little Ice Age viscosity structure. And so if we want to know how much sea level is going to change in Greenland by 2100, we really need to understand the history of ice change, both on the longer time scale from the last glacial maximum to today, but then also the more recent shorter timescale event too that occurred during the Little Ice Age, and consider that they might induce different viscosities in the mantle. And so with that, I'll just get into our approach a little bit of how we did this, how we created our projections of sea level. And so we first did assume those two separate viscosities for the two different timescales. We assumed a larger 3D viscosity for the last glacial maximum, and then a smaller 1D viscosity for the Little Ice Age. And to include the last glacial maximum in our projections, we used a suite of already published 3D GIA models. So we didn't run any new 3D GIA models. They actually take a good amount of time to run. We just used what was already published in the literature. However, to include GIA from the Little Ice Age, we did run a suite of 1D GIA models forced by Little Ice Age mass changes that we obtained from this study done by Adhikari et al. And the time series of that ice change is shown in this figure on the right. And then in our GIA models, we varied for different parameters: the Little Ice Age termination time, Little Ice Age mass anomaly, a lithospheric thickness, and then the mantle viscosity. And just noting that for the mantle viscosity, we used a lower range than compared to the steady state viscosity that's typically assumed, which again is around 5 times 10 to the 20 to 10 to the 21. And so we use a lower range to approximate that transient response for this shorter timescale event. And our first step that we did was using these GIA models to predict present day vertical land motion in Greenland, so present day uplift. We ran a total of 14,040 models to explore the parameter space. And then to further constrain these parameters, we compared our predictions to observations that we obtained from the 55 GPS stations that span Greenland's coast. And we did this using a Bayesian approach that essentially picked a model, assessed the fit of the predictions to observations, and then weighted that model more heavily in our posterior if it was able to fit the predictions well, or the observations well. And so in our posterior, we found that we were better able to fit observations at the majority of stations, and found that we had a decreased variance at all stations. And this is not something that is super impressive or surprising. Again, we basically weighted those models that were able to fit observations more heavily. So this was more of just a sanity check that we didn't screw something up in our Bayesian analysis. The figure on the left here shows our posterior average of present day uplifts just caused by the Little Ice Age. And so we can see in this figure, red indicates uplift and blue indicates subsidence. And so we can see that we predict uplift everywhere in Greenland caused by the Little Ice Age, with rates reaching up to 6 millimeters per year along the southeast coast where uplift is greatest. We can also look at different parameter combinations that we varied in our GIA models. This one shows specifically the solid earth parameters. And in this figure, yellow indicates that those parameters, when used in our model, were able to make predictions that fit observations better. And we found that we have a preferred viscosity. So our best fitting viscosity is around 6.3 to 7 times 10 to the 19 Pascal seconds. And then we have a preferred lithospheric thickness of around 220 kilometers. And both this lower viscosity and higher lithospheric thickness are indicative of transient rheology below Greenland. Okay, so finally, we use the models that were best able to fit predictions to project sea level out to 2100. And we did this by forcing those GIA models with projections of ice sheet change from both Greenland and Antarctica for RCPs 2.6 and 8.5. This figure here shows a spatial plot of our sea level projections at 2100 for both RCPs 2.6 and 8.5. And this includes the contribution from the deglaciation, the Little Ice Age, future ice melt, as well as projected contributions from thermal expansion, ocean dynamics, terrestrial water storage, and global glacier change that we obtained from the IPCC 6th assessment report. So in these figures, blue indicates a sea level fall. And we predict sea level to be falling everywhere along Greenland's coast by 2100. And we find that the largest contributor to the sea level fall is actually GIA driven by ice melts that occurs in the future. Although GIA caused by the Little Ice Age is non-negligible and in some areas can reach 0.3 to 0.4 meters. We find that the contributions from thermal expansion, ocean dynamics, terrestrial water storage are positive everywhere. So they cause sea levels to rise everywhere, which combats the sea level fall driven by ice change. And then the contribution from global glacier change is mostly positive everywhere, except for the area on the northwest coast where we get sea level fall caused by melt from Arctic Canada. We find that sea level could fall by as much as 2.8 meters by 2100. And that's for RCP 8.5. But this is a significant amount of sea level fall. And not only will it affect the communities, as Margie talked about, and I will also talk about in a second, but it can also affect the dynamics of the ice sheet itself. And so I'm just going to talk about that first before I dive into the communities. Specifically, relative sea level fall of that magnitude could act to stabilize marine terminating outlet glaciers in Greenland. And so this figure on the right shows ice velocity for the Greenland ice sheet. And I'm really only showing this to highlight the 3 marine terminating outlet glaciers where we project a large amount of sea level fall at 2100. So this is the Kangerlussuaq Glacier, Helheim, and Jacobshavn-Easbrey glaciers. And so for a marine terminating outlet glacier, the grounding line denotes the point where it begins to float, and the ice flux across the grounding line is really strongly dependent on how thick the ice is at the grounding line. So if you have thicker ice at the grounding line, you get more ice flux across it. And yeah, if it's thinner, less ice flux. So if you have a marine terminating outlet glacier that sits on a retrograde slope, so one that gets deeper as you move inland, as that glacier retreats, the thickness at the grounding line increases, causing the flux to increase. And so this creates like a positive feedback loop that can just lead to the glacier melting more. However, if GIA can occur quickly enough, it can raise the bed at the grounding line, causing it to advance outwards, causing the grounding line to advance outwards. And this decreases the flux and can act to stabilize that glacier. And a study that looks at this in Antarctica finds that uplift of 1 to 4 meters by 2100 can act to stabilize certain sections of the Antarctic ice sheet. And we see a similar magnitude of sea level change here. And so a next step, which I'm not planning to do, but would be really cool, would be to run a coupled GIA and ice sheet dynamics model just to see if we do see this effect occurring over the next century. Okay, now on to the communities, as this is the more important part of this project. Again, Margie gave a really great introduction on us working with these 3 communities and why sea level, any changes in the marine environment will be impactful to them. So this shows, sorry, very loud siren if you can hear it. This shows projections of sea level fall for those 3 communities, Osiat, Nuuk, and Glacial, out to 2100 for RCP 2.6 in the blue and RCP 8.5 in the red. And then the chart shows our projection at 2100 in meters. And so we can see that sea level is projected to fall in all 3 of those communities. I really wanted to show this just to highlight the difference in sea level fall that you can see at each community. So for example, for Glacial, we see a fall of up to 1.3 meters, whereas for Nuuk, we get less of a fall of around 0.8 meters. And so it's not just that having projection, like one projection for Greenland would be enough, but having projections for each community and looking at the impacts of that amount of sea level fall for each community is really important. And so just zooming in onto the impacts of sea level fall for one community, I'll be looking at Osiat, which is located on the western edge of Greenland. And in Osiat, sea level is projected to fall by about 0.9 meters. And so this map here shows a combination of the bathymetry that we mapped during the Greenland Rising Project, as well as, or combined with our projections of sea level fall. And so colors indicate the bathymetry, and then in the panels C through F, you can see these areas that are shaded in dark gray, light gray, and white. And these areas indicate places that will become exposed at low tide for different emission scenarios. So dark gray is areas exposed at low tide for RCP 2.6, light gray for RCP 8.5, and then white for our highest projection for RCP 8.5. And so just zooming into the harbor in Ossiat, which again, Margie talked about how fishing and hunting is very important in Ossiat. And so any changes in the harbor can really affect the people there. And we can see that there will be areas exposed at low tide at 2100, especially for RCP 8.5, but even for RCP 2.6. And so having shallower waters in the harbor can make these areas more difficult to navigate, especially for deeper draft boats. Shallowing waters can also cause stronger currents, which again makes it harder to navigate. Another area of concern for the people of Ossiat was this Nevok channel, which is shown in panel F. And this channel connects smaller coastal communities to the east with the larger commercial hubs of Ossiat and Ilulissat. And we can see that even just for RCP 2.6 at 2100 during low tide, there will be large portions of this channel that are exposed, making it inaccessible to navigate through and forcing boats to take longer offshore routes instead. And so, again, just wanting to highlight what Margie really said was that people that live in these communities and these towns really do interact with their marine environment on the daily. And so any changes in sea level will be impacting these communities. So with that, I'll just leave my conclusions up here because I know that we want to leave some time for questions. But I would like to highlight the collaborators on this project, especially my PhD advisor who helped a lot with this work, but then everyone else, and then especially our collaborators in Greenland, Carl and Akaluk, because they've been amazing, and the rest of the Greenland Rising team. This has been a super fun project to work on during my PhD. Yeah, thank you guys for listening.
Great, thanks. So we have 4 or 5 minutes, I think, for questions. One quick one has come in already is just, can you give us a little reminder of the difference between, or what RCP 2.6 and 8.5 signify, and maybe like warming levels or something?
Yeah, for sure. Sorry, let me just, yeah, so RCP 2.6 is like the lower end emission scenario. And I think it means that we keep our emissions constant until 2050 and then begin to reduce them, or something of the sort. So it means that we will have a reduction in emissions out to 2100. RCP 8.5 is like very high end emission scenario, like basically business as usual, and even more like, yeah, we just continue emitting. Yeah.
Cool. I've got a question I can throw in here while people are entering anything else in the Q&A box. Just a little curious, the GIA like modulated by viscosity and then the gravitational effect, like this can get really complicated. So I'm curious how difficult it was to explain kind of this idea of local sea level fall when you're talking with these communities, or like is it actually pretty easy and you can gloss over those details because like the observations and the history kind of make that intuitive for them? Or what strategies did you find helped you kind of get this complex stuff across?
I will say one thing, but then I'll maybe pass it on to Margie because she worked a lot with the education things. I think there is a lot of obviously like complex stuff going that concerns GIA, but I do also think it can be quite a simple topic to explain, like just saying like, oh, the ice melts and it causes land to rise because of the reduced weight, and that causes sea level to fall. And I think that was like something that was kind of intuitive to get across, like once you explained that. And we also had this project that had to do, we used goo, glacier goo, we called it. And it's basically like silly putty, and that's like a really great analog for the mantle. where you just place something heavy on it, it sinks down, and then you take that off and it begins to rebound back upwards. And so that was something that was really helpful, and also a really fun activity for the schools that we went to in Greenland. And I don't know if you have something else to say about that, Margie, but
Well, I
yeah.
will say that actually that activity is one that UNAPCO also uses. So I do I do recognize that that is one that they have a similar one posted on their website. We Akaluk is a geophysicist, and so he was huge in terms of our ability to be able to have these discussions at both the community level and in the classroom level. We developed an entire set of curriculum around the adjustment of the earth, as well as the attraction of the ocean and the detraction as that ice is reduced and the gravitational attraction changes. And his ability to, we do a lot with our hands-on and with gestures, but his ability as a geophysicist to kind of take things into a fairly simple communication piece was huge. They don't have a lot of words. So, one word can be an entire sentence. And they don't have a lot of science words that we actually had them add some words to their language because they didn't have words to explain some of the things we were talking about. So that in itself was a really interesting thing and a really fun thing to have the opportunity to have that discussion and see these new words become part of their general overall language. I'll leave it there.
We have 2 more questions that are in already, so I think we can maybe get these if folks can stay on for a couple minutes past the top of the hour, and then we'll get you out of here. So one question is, was INSAR used in some of the inputs for measuring how the land surface is moved or things like that?
I did not use any INSAR. The only observations that we used for the vertical land deformation was from the GNSS stations. So yes, I did not use INSAR. I don't know if Kirsty if that was used elsewhere in the project, but not for me.
Yeah, not that I'm aware of, no.
Okay, thanks. And then another question, the way that the sort of the physics of viscosity affecting over these different time frames, is that, the question is that more variation of viscosity like with depth or horizontally?
Yes. So I think it can be both. As I showed in this figure, we do see variations just like in the radial structure, but also laterally as well. And I think the main change in viscosity that it causes is more in that like what we consider the steady state viscosity to be over that time scale. So like over a long time scale, we generally assume like a very high viscosity, and that's generally a correct assumption. But then as we move to these lower time scales, that viscosity that we would use decreases. And so I guess the answer is I think it can change both laterally and with depth. But yeah, I think the main thing to think about is just like what is that like steady state viscosity that we would use for that time scale. Yeah, sorry. I don't know if that answered the question, but
Hopefully. Okay, one more question snuck in I think we can get. If you can go back to the projection plot for the actual ground motion, maybe for the 3 locations, the 3 towns.
oh yes.
Yeah. The question is, so you mentioned like 2.8 meter fall, for example. What's the sort of range of uncertainty on that?
Yeah, so it's about like half of a meter, I would say. Plus or minus half of a meter of uncertainty on that fall.
Okay.
Yes.
Hopefully that answers.
I'm like second guessing myself, but I think that's correct.